Hi, my name is Michael Wong. Welcome to everyone at this IWOCL SYCLcon 2021 and everyone viewing this in the future through the internet land. I am the chair of the SYCL working group in Khronos. And today, I'd like to talk about three things: SYCL's insanely enormous growth in momentum, what is in SYCL 2020 and the future, and three, SYCL as an open offload programming model for high performance computing. So SYCL 2020 is here. SYCL 2020 is released after 3 years of intense work, and significant adoption has existed now in embedded, desktop, and HPC markets. There's improved programmability, smaller code size, faster performance, and it's based on C++17, backward compatible with SYCL 121, simplify porting of standard C++ applications to SYCL, closer alignment and integration with ISO C++, multiple backend acceleration, and API independent. SYCL 2020 has increased expressiveness and simplicity for modern C++ heterogeneous programming. I want to point out the incredible SYCL industry momentum in recent years. Most recently, you might have seen the next platform asking, can SYCL slice into supercomputing? And that is based on the announcement of the collaboration with NERSC Argonne Leadership Computing Facility on SYCL on the Perlmutter supercomputer. Before that is SYCL and DPC++ on Aurora. DPC++ is the Intel One API implementation on SYCL you see on the top right. There's the NSI Tech's Kyoto microcomputer joint work using SYCL on the RISC-V vector system. There is Tricycle for Xilinx FPGA work from University of West Scotland. There is the Renesas Codeplay collaboration using SYCL and OpenCL on their RCAR ADAS solutions. There is the HPC implementation for AMD ROCm CUDA GPUs. There is the TensorFlow native support on PowerVR using optimized SYCL libraries. So what is SYCL 2020? SYCL 2020 is the newest release of the SYCL specification ratified by the working group in late 2020, published by the Khronos group in early 2021. It follows SYCL 121, the last version to be based directly on OpenCL, previous release following SYCL OpenCL-based release. And in light of the move to a more generalized backend model, as well as following ISO C++ release based on the year, the project has adopted a year-based versioning scheme. SYCL 2020 presents it's a major step forward, featuring over 40 new additions and improvements, including unified shared memory for pointer-based programming convenience, parallel reductions, workgroup and subgroup algorithms, improvements to atomic operations, class template argument deductions or CTAD, and deduction guides, simplification of accessors, expanded interoperability with different backends. We now have an updated FAQ and Wikipedia entry reflecting SYCL 2020. There will be even more in-depth Wikipedia page on SYCL coming in the future, listing all the known projects, research, and tutorials. So this slide introduces how SYCL fits for working with different libraries, machine learning frameworks, and standard C++ code on top of template libraries with Lambda functions that separate hosts and accelerate device code in a single source, but still enable separate compilations of hosts and device code. The device SYCL compiler can employ kernel fusion for better performance, and the host CPU compiler can be any C++ compiler from Clang, GCC, Visual C++, or IBM's XL compiler. All these enables accelerated code to pass in the device OpenCL compilers or other backends to dispatch to any variety of devices. This slide is about parallel industry initiatives. and the possible future roadmap of SYCL, where we release SYCL 2020 based on C++ 17. This means it enables exciting C++ features such as class template argument deduction and deduction guides that makes code less verbose. There are also a number of other great features which I will highlight. You're going to see that we released SYCL 121 in 2017 and previously 1.2 in 2015. And if you were to predict that we seem to be settling down to a cadence of releasing new release every 1.5 to 3 years, matching to the ISO C++ schedule, you will be right. This is because we have adapted to a bus train model of delivery. You will also see that we have changed the naming scheme from aligning with OpenCL versions to naming by year to allow us to be based on multiple backend options in addition to OpenCL, which remains our primary backend. You will also see that we are projecting tentatively that a future SYCL next will be released after 2021, the exact version to be named later, and will likely be based on C++ 20, which will be released at the end of this year. This shows our tighter ISO C++ alignment, injecting our heterogeneous knowledge into ISO and adapting C++ features. This is the main slide. It shows what is in SYCL 2020 on the bottom left. You're going to see some of the 40 features that we have. And in the top left box, our general philosophy of that we have followed in our change from SYCL 121 to SYCL 2020. We want easier integration with C++ 17, less verbose language that has smaller code size, and simplify common patterns. We wish to enable multiple backends, but simplify interoperability, while at the same time ease porting of common C++ applications to SYCL, improving programmability. We want to strike a balance for performance and stability by enabling backwards compatibility with previous releases, but also selectively break API to achieve better performance. We expect that breakage to be minimal from SYCL 121 to 2020. On the top right, you're going to see all the talks and events at SYCLcon 2021. I remember when we first started this as a workshop called HPC C++, and along with the SYCL group, wrote most of the papers and talks 6 years ago. Now we have most talks are written by non-SYCL working group members, and that's a great thing. What a growth and achievement we've witnessed. In the bottom right, you're going to see that what we have to do next in the form of conformance tests and working on conforming implementations, as well as the new SYCL next feature proposals. And on the far right, you see that our main goal is converging SYCL and ISO while continuing to strongly support OpenCL, driving to support even more kinds of chips. The main diagram with the arrow shows, basically illustrates our philosophy of moving from SYCL 2020 to SYCL next and iterating the cycle with new releases every 1.5 to 3 years from previous to next release. Now, this is a snapshot of the SYCL implementations as of April 2021. In addition to the usual Intel DP++, Codeplay SYCL, Xilinx's TriCycle, University of Heidelberg's HPCL, we have a new implementation from Japan called NeoSYCL from University of Tsubasa on the NEC vector offload engine. More about this later. So SYCL momentum has been huge on all fronts in the last 6 years, but especially in the last 2 years. This is a chart of many of the open source public GitHub projects that are showing the growth of Intel's Clang LLVM port in blue, of course, HPCL in red, TriCycle in pink, Celerity in green, and SYCL GTX from Peter Zuzak, who now works at Codeplay, in yellow. The other graph shows the growth in the number of Stack Overflow questions from when I started in 2016, when there were 7 questions, to 70 this year after 6 years. It's a 10 times growth. The number of people attending the working groups has doubled, and it has doubled as well. And that's really thanks to contributions from an insanely talented group of dedicated people across many companies, some of which you're going to hear in this conference talking about SYCL features, SYCL projects, and SYCL research. I'm so grateful for all the help this group has done to build this SYCL momentum. And they are also the nicest bunch I have worked with in my several decades career in working on many different consortiums and standard organizations. So this highlights the already large and growing SYCL ecosystem, starting with the implementation on the left, including, of course, the new NeoSYCL. Then there are the many research papers. Of this, I have talked about the exascale computing project and Celerity for SYCL cluster last year. These projects allow SYCL to run on exascale and petascale supercomputing systems. Coco and Raja C++ are performance portability programming frameworks for C++ parallel executions and memory abstraction. One of our working group member, Nevin Lieber, is working on delivering SYCL on Cocos. GROMACS is a molecular dynamics package mainly designed for simulation of proteins, lipids, and nucleic acids from Stockholm University. And that is also a spec CPU benchmark and is now being accelerated for SYCL. The Alpaca library is a header only C++14 abstraction library for accelerator development from HZDR and LPNL. TaskFlow is a general purpose parallel and heterogeneous task programming system extending for task graph parallelism for distributed and heterogeneous nodes from University of Utah's Professor Wong. The ATLAS experiment, or Athena, is a high energy physics experiment looking for Higgs boson and quarks from CERN. And recently we had 2 talks in GTC 2021, we never thought we would have them there, by Brandon Cook from LBL and NERSC, and Peter Boyle of University of Edinburgh. The next column are benchmarks and books. We have direct programming benchmarks, which is a collection of data parallel programming for evaluating one API direct programming. Each program is written with CUDA, SYCL, and OpenMP 4.5 target offloading. We have SYCL Bench Suite, which is a versatile cross-platform benchmark suite for heterogeneous computing from University of Salerno, University of Heidelberg, University of Innsbruck. We also now have a one API SYCL book published by James Rinder, whom you will hear or heard on a keynote, with members of Intel's team. All have been good friends that I have worked with, some for decades. There are also many libraries for linear algebra, machine learning, and parallel acceleration frameworks, now separated into what domain they serve, including BLAS, fast Fourier transform, math, random, solver, sparse matrix, tensor, and STL. At the bottom, you'll see the working group companies attending the weekly call, which are 1 or 2 times a week. Here, I want to show some common use cases and how SYCL is being used in those domains. Here we see how Khronos standards can be used in a typical mobile or embedded application needing vision or inferencing acceleration. Neural network training typically occurs on high-powered desktops or servers at high precision using large training data sets. The resulting training network is encapsulated in an NNEF or ONNX file and can be imported into the target system in 2 ways, either ingested into an inferencing engine such as OpenVX or passed into a machine learning compiler to generate code that executes inference operations. Either the compiled code or the inference engine API is linked into the application, which may also use the SYCL compiler to generate additional parallel code if the application is written in C++. Code generated by all these methods can target the lower level OpenCL API to portably reach into diverse hardware processors. Now, we are also going all in on safety critical, ethics, functional safety, AI, ML safety. So SYCL, like OpenCL, aims to serve the embedded automotive AI domain with safety critical in the future, just like other current efforts by the United Nations Economic Commissions for Europe, UNECE, WP29, like Khronos APIs, or by being part of RISC-V, MISRA, ISO SC42 on AI ML trustworthiness and ethics, safety of machine learning, ISO 26262, 21448, functional safety and safety of the intended functionality, Safety Critical Systems Club, UL 4600, and SAE's ORAD. So this is one of the talk this week outlining an initial proposal on autonomous ADAS safety built on a tower of overlapping safety layers from the application to the library on top of SYCL over a hardware abstraction layer or down to the hardware driver. So here are some SYCL customer quotes using SYCL for embedded, automotive, AI, and safety from Renesas, from Xilinx, from NSI Text, and from Imagination. So now we turn to look at how SYCL is used in HPC and what distinguishes us from other common HPC language. So HPC workload generally persists for 20 years, while the hardware can change every 5 years, often to different vendors. They need to serve the 3 pillars of science problems across the top. Simulations, which needs an HPC language with solvers and parallel runtime. Data science, which needs a high performance, high productivity language for big data. There's also machine learning, needing a high productivity language for machine learning. So these generally have been supported by the top 3 set of languages like OpenMP, mostly for C and Fortran, a mix of CUDA, OpenACC, OpenCL, and now for C++, SYCL, Khronos, and Raja. So on the right, you see the development workflow for these science problems. And it starts with number 1, choosing an algorithm. Unlike before, today, that choice needs feedback, knowledge of the system architecture and tools. And these tools need to have control of the data layout, movement, locality, and affinity, or they will not be performant. SYCL and other C++ frameworks enable these parameterization and dynamically configured algorithm through C++ capabilities like templates and inlining, unlike other language which are not able to do that. So the second thing they do is, of course, they implement and test the algorithm. And then the third thing they do is they optimize the algorithm. Now, traditionally, this was the only step that needed architecture and tool knowledge, but not today. Today, it needs to be known at step 1 when you're choosing the algorithm. So all these steps enable us to reach performance portability code. They are required to reach exascale computing for the 4 major systems, of which 2 are now SYCL, ANL's Aurora, and NERSC LBL's Perlmutter. And the other 2 are AMD systems, Frontier and Al Capitan. And SYCL has demonstrated to work on AMD systems as well. This parameterization and dynamically composed algorithm, along with compiler optimization using an open standard programming model, is what we think will enable performance portability and make SYCL stand out from the other languages. Next is here are some of the SYCL customer quotes using SYCL for exascale computing or pre-exascale computing from Argonne and Chineka. And here are some SYCL customer quotes using SYCL for high performance computing from the University of Innsbruck, University of Salerno, NERSC LBL, and Intel. So SYCL has had insanely phenomenal growth in the last 6 years. But what now? What is there in the future? Well, we like to take a look at deep diving into high performance computing. So HPC, exascale computing, requires programming models that endures for future workload lasting 20, 30 years. But the hardware changes frequently with constant improvements. And there's usually a mandate for sharing the diverse hardware across a large consortium of universities and research labs. The programming models have to be stable, but also driving to support the latest hardware. They must be open, can't be closed, and it covers multiple architectures because you're constantly computing on multiple systems. And there needs to be multiple implementations to verify and check each other. So in order to do that, to support that, we need parallel heterogeneous future hardware This is in the background here. I know it's hard to see under the words, is the TIOBE index of programming language, and see how they've grown over the year. And the little black line you see there is actually Java, which is now decreasing, so that C, Python, and C++ in blue, green, and orange is now reaching the top. So as a result, there's a great love for the ISO standard languages like C, C++, and Fortran. And also OpenMP is great as a parallelization for C and Fortran. And SYCL is great for modern C++, AI, automotive. And here are some opportunities for high performance computing growth across Europe and Asia. Let's have a look. So here is the future of the future in HPC, and it's tightly coupled with machine learning and AI because they're enablers for each other. There's some autonomous vehicles, embedded systems, FPGAs that are just essentially now HPC systems. HPC has strong focus on climate, urgent or pandemic computing, and fake news detection, AI, autonomous vehicles, finance, quantum, and big data. So 6 months after starting up the European Processor Initiative, EPI, has essentially delivered its first architectural design to the European Commission, essentially completing the first phase of the project. The goal of the initiative is to create a new family of low-power European processors, primarily aimed at high-performance computing, the first of which is slated for 2021 now. EPI wants to establish itself as a new commercial entity. Hence, the platform was conceived with economic viability in mind. To that end, the technology is not just limited to HPC and AI, but it also wants to cover other applications such as the data center and the automotive sector. For the latter segment, it wants to develop customized processors to meet the requirements for autonomous cars. The first family, codenamed RIA, will come to market in 2021. It's going to contain both ARM, RISC-V, and external IPs. It will serve as the basis for a European pre-exascale system and will also include an automotive proof of concept. EPI also plans to deliver the second family, Khronos, in 2022 and 2023. It will be used for the European exascale system and include an automotive CPU. Now, the project to build the first European HPC system consists of two streams that will generate a heterogeneous CPU, a general purpose microprocessor stream for a low power ARM-based HPC CPU, and an accelerator stream. There's also an automotive platform stream that is a significant part of the technology, definitely will be European. The accelerators in particular are seen as crucial to improving performance and reducing power consumption. EPI has described two kinds of accelerators, one based on the open source RISC-V instruction set, and another one based on Khronos IP, a French company that builds many core processors based on the very long instruction word, or VLIWISA. You heard one of the, you're going to hear one of the keynotes this week. The RISC-V technology will be used to build multiple accelerators for HPC and AI, such as a vector processing unit, a stencil tensor accelerator or STX, and a variable precision coprocessor. The Khronos accelerator, on the other hand, is aimed at a deterministic automotive computation. The common platform on the right is conceived towards the heterogeneous future and with the concerns of high bandwidth and efficient data movement. In particular, the package consists of two chiplets, likely the ARM-based general processor and either the RISC-V-based accelerator of HPC or the Khronos accelerator of automotive, and several stacks of HBM memory connected via an interposer. In June 2019, the Euro HPC Joint Undertaking Governing Board selected 8 sites for supercomputing centers located in 8 different EU member states to host the new high-performance computing machines. The hosting sites will be located in Sofia, Bulgaria, Ostrava, Czechoslovakia, Kazani, Finland, Bologna, Italy, Bissen, Luxembourg, Minho, Portugal, Maribor, Slovenia, and Barcelona, Spain. 3 of the 8 sites are going to host precursors to exascale machines that is capable of executing more than 150 petaflops, or 150 million billion calculations per second. And that will be in the global top 5 supercomputer, and 5 petascale machines capable of executing at least 4 petaflops. The precursor to exascale systems are expected to provide 4 to 5 times more computing power than the current top supercomputing systems of the PRACE, or Partnership for Advanced Computing in Europe. Together with the petascale systems, they will double the supercomputing resources available for European level use, meaning that many more users will have access to them. And then also in Asia, we have exciting news with a SYCL implementations for SX Aurora Tsubasa on an NEC vector offload engine, showing essentially no loss in performance from using SYCL in the middle graph on the left versus a native VEO offload in the third graph on the left using Rodinia benchmark on breadth first search. It also shows programming with SYCL leads to lower code complexity in terms of lines of code in some cases. The final things, the things I want to leave with is that SYCL can be a part of a standard programming model for all HPC, including Europe and Asia, as well as the North America. HPC is now used essentially in embedded and automotive. SYCL is homegrown EU. UK companies led its development since 2012, but now it's an open standard with multiple company contributions. Lots of European Asian projects, like Celerity from the University of Innsbruck and Salerno, Chineka from Bologna, and NeoSYCL in Asia. It moves with ISO C++, updates every 1.5 to 3 years. It's part of one API with a large ecosystem of libraries, adapts to high performance computing hardware changes, and is moving towards safety critical. It's adapted by ECP for the first exascale computer in Aurora, now also in Perlmutter, and we are also aiming to be programming models for Europe and Asia. Last two slides is going to show how we enable industry engagement with feedback, as well as what features. And this is showing you how you join SYCL. Membership is open to all, and 3 of these don't need any money, including working on the public GitHub, public contribution to specs, and being part of the advisory panel. The advisory panel is now chaired by Tom Deacon from University of Bristol, and there is a advisory panel meeting here at IWOCL SYCLcon on Tuesday. Only the working group is needed if you want to know the secret sauce. The last slide is going to show that SYCL is creating cutting-edge, royalty-free, open standard for heterogeneous C++ compute, vision, and inference acceleration. I am Michael Wong, chair of SYCL, and I encourage you to join Khronos and SYCL with increased expressiveness and simplicity for modern C++ heterogeneous programming. Thank you.